Okay guys, let's take a look at today's lesson. We're going to be working with calculus topics today, mostly with rationals, but we're working with calculus topics today. These are topics that we, do in calculus. Yay! So let's take a look. We have basically two things we're going to be working with. We're going to be working with limits to infinity, so limits at infinity, and we're going to be working with making an integral that we have look like a formula. So that's a concept that we do in calculus, is to rewrite something so it looks like a formula that we can use. And so those are the two things we're going to do today. This formula may seem like, oh my gosh, what's she talking about? But really it's the easiest thing on the lesson. So we'll do that second. The first thing we'll do is talk about limits at infinity. We have talked about limits before when we were in our trig stuff. We were talking about, we did limits of trig functions. Remember that? We would do, we had special trig limits. We would sometimes graph. We would sometimes do it algebraically, but we have experience with limits. Today we're taking it just a step farther, and we're going to be looking at what happens when we basically x goes to positive or negative infinity. What do we do? And so this first part right here, definition of limits at infinity, really is just notation, just looking at notation. If f is a function, L1 and L2 are real numbers, then this just telling you how this statement looks and how to read it. This is really all this first thing is doing. So the first statement is read, the limit of f of x as x approaches negative infinity is L of 1. That's talking about this second statement. Okay, that's just notation. There's really nothing to memorize or there. It's just how would you say it. Let's talk about the real meat of it, and that is using, these are special limits right here. These are special limits that I'm going to talk about and kind of get our mind wrapped around them. So n is some positive real number, 2 or 25, it doesn't matter. What this is saying, let's kind of conceptualize what this is saying. As x heads to positive infinity, as x values get larger and larger, the denominator is going to get larger and larger, right? So I have a stationary number, 1. It doesn't have to be 1. It could be any number. It could be a million. It doesn't really matter. Any number. Think about 1 over 100, 1 over 1,000, 1 over a million, 1 over a billion. Do you see what's happening to this entire fraction when the denominator continues to grow without bound and the numerator is stationary? This fraction tends, T-E-N-D-S, that's a phrase we use, tends to 0. So what that might look like, with the rationals that we've been graphing, it might look something like this. The rational just keeps going and going, and it just keeps, as x gets larger and larger, y gets closer and closer to 0. So that's what this concept is. We're going to be using this concept to help us solve limits to infinity. Likewise, same thing can happen when we're going to negative infinity. Think about that. If I have 1 over negative 100, 1 over negative 1,000, 1 over negative a million, right? 1 over negative a billion, this fraction is going to get closer and closer to 1. Now, with a limit, we need to understand that it doesn't have to actually equal 1. It just has to get closer and closer. It has to approach 1 or 0. In this case, 0. It has to approach 0. It doesn't have to actually equal 0. That sometimes troubles students. They're like, well, I don't really like that. It's not going to ever be exactly 0. No, and it doesn't like it either. It's very sad about it, by the way. It's never going to actually get to be 0, but it tends to 0. It approaches 0. Okay, so these two special limits we're going to use to help us with problems. That's on the next slide. So the other thing we're going to talk about that has to do with limits to infinity is I explained when we were working on horizontal asymptotes. Remember that at the beginning of the unit? I said there's a Precal way and there's a calculus way. Well, the Precal way we went over and we've practiced that. This is the calculus way. So if we want to find a horizontal asymptote, this is what we would be doing. We would take the limit to positive or negative infinity and get our asymptote. Remember the horizontal asymptote, see how it's y equals? That's the equation of the horizontal asymptote, y equals a. So whatever these limits, whatever the answer to these limits is, then basically our horizontal asymptote would be y equals whatever that number is. That's how we find horizontal asymptotes. The calculus way is we use, this is the definition of a horizontal asymptote. Basically, we are taking the limit of our function to positive or negative infinity, and we get our horizontal asymptote. Okay, so that's what we'll be looking at today. So let's look at these next three. These are formulas. I don't have what this equals, but I will tell you this integral is going to give us a form of arcsine. Remember our little friend arcsine? See how important it is in calculus? It just pops up, right? I see how nice I am to y'all by making us do trig all the time. You're like, yes, that's so nice. This one is going to be, once we integrate, it's going to be arctangent, a form of arctangent. This is going to be a form of arcsecant. So they are a very big deal to us in calculus. So what our goal is, these are the formulas to create, to integrate things. We need to, I have a couple of examples on the other slide where we take what we are given and we make it look like this or this or this, whichever one it matches closest. Okay, so that's just a, we want to make the expressions look like the formula so that we can integrate it with the formula rather than any of the many number of different ways we're going to learn to integrate. Okay? So that's basically what we're looking at today. So let's turn to the next page. Let's go to the next slide and do some examples. Okay, so the first one, we're going to, the first three examples are limits to infinity, positive or negative infinity. So we're going to work through those. And the technique that we're going to use is we're going to use that special limit. I'm going to multiply, of course, I hope we understand, on a limit, we can only multiply by the number 1. We are not allowed to multiply by like anything else, just 1. So what I'm going to do is I'm going to look in the numerator and denominator. I'm going to determine what the highest power is. It's 2. And I'm going to multiply this by 1 over x squared over 1 over x squared. Now we do this in calculus. We do this very same thing in calculus, and I'll tell you that some students still get confused about it. So I'm hoping that the more you see it, the less confused you will be. So I'm going to distribute this 1 over x squared to each term in the numerator and denominator. So the limit as x goes to negative infinity of, so I have negative 2x squared over x squared plus 3 over x squared. That's what I have in my numerator after I distribute 1 over x squared. Let's do the same thing to the denominator. So I have 3x squared over x squared plus 1 over x squared. So my first step is just to distribute the special form of 1 that I created. Now we're going to simplify it, clean it up. So we say the limit as x goes to negative infinity. Now cleaning this up, we see that x squared over x squared goes away. I'm left with a negative 2 plus 3 over x squared, there's really nothing I can do to simplify that, over. So we have 3x squared over x squared, that simplifies to 3. And then 1 over x squared, there's really nothing I can do to simplify that. So hopefully you remember from your limit days a few months ago that the limit laws are quite flexible. I can do the limit of each thing independently. Right, I can rewrite it like that. I'm not really going to go to that trouble to rewrite it, but I want you to think that I'm taking the limit of each one independently. What I typically do is I notice that that's just a negative 2. It's just going to be a negative 2. This one is a form of the special limit on the other page, right? It doesn't have to be a 1 in the numerator. It could be any number. So what's going to happen as this bottom number grows without bound, this entire fraction is going to tend to 0. And what I normally do is I just circle it to show myself that it's 0. That's like zeroing it out for me. We look in the denominator, we see there's nothing to do with 3, but we also see this is a special limit, and that's going to zero out. So our answer is basically what is left over, and our answer is going to be negative 2/3. Now for pre-calculus, we're just kind of stepping into this. I want you to show this work every time, this multiplying by the special 1 every time. Once we get to calculus next year, you'll be able to perhaps do it a little bit of a different way, a little bit quicker, just seeing things. But I want us to kind of just work through the process this year to get it kind of solidified in our brain of what's actually happening. And that's what's actually happening. Okay, if we were asked to find the asymptote, the horizontal asymptote of negative 2x squared plus 3 over 3x squared plus 1, we would have done much the same thing, wouldn't we? We'd have taken the limit to infinity and we've gotten this. Our asymptote would have been y equals negative 2/3. Right, that's what we would have done had we been asked for the horizontal asymptote. Okay, questions so far? Are we okay? Okay, let's move to the second one. So I look at this and I see that cubed, the 3 is the largest one, so I'm going to multiply by 1 over x cubed over 1 over x cubed. So that gives me the limit as x goes to negative infinity of, so I have negative 2x cubed over x cubed plus 3 over x cubed. That's what I have in my numerator. Now I'm going to distribute the denominator. So that gives me 2x squared over x cubed plus 1 over x cubed. Okay, I'm just distributing here. Now let's clean that up. Let's simplify that. So I have the limit as x goes to negative infinity. So we see the x cubed over x cubed goes away. I'm left with a negative 2 plus 3 over x cubed. Really nothing I can do with it. Go to the denominator. In the denominator I have x squared over x cubed, so I know I can simplify that to be 2 over x plus 1 over x cubed. So everything is simplified. Okay, we okay? So now let's do our special limit. We know that this is going to go to 0, right? We know that this is going to go to 0 and this is going to go to 0. So I basically have negative 2 over 0. That's a bit of a problem. That's not an answer. It's not a real answer. Right? If it was 0 over 0, that would be a different issue. That's an indeterminate form. We're really not going to be dealing with that very much here. But a number over 0, there's only two possible answers for this, and that is positive or negative infinity. That's it. So what we have to do when we get something weird like that is we have to look back and see, well, which one is it going to be? Now, it's a 50-50 chance if you just want to guess, right? Oh, I guess it's positive infinity. I guess it's negative infinity. I mean, there's only two answers, two possible choices. But let's kind of approach this a little bit more logically. How are we going to find that out? So we're going to go back to the original expression, and we're going to really think through it. You're going to have to think. So I've got a negative number, really big negative numbers. If I put a really big negative number in here, what is this going to turn out to be, a positive or a negative number? It's going to be positive, isn't it? Because a negative times negative is a positive. If I put a really big negative number down here, what is that going to turn out to be? Positive. So am I going to be going to positive or negative infinity? Positive. I mean, right? It's my only choice, right? All the numbers are positive. So my answer is going to be positive infinity. Okay? That's the answer. The answer is not negative 2 over 0. That's meaningless. It just means that it's not defined. It's an undefined number. That is where we're going, is a positive infinity. Okay? All right, so this next one still gives some of my calculus students fits. All right, so I've got to go to the concept behind it before we work with it, because this is kind of a really big deal. So we really have to look at two different things. One is what the square root of x squared equals. Now, many people believe that the square root of x squared is x. Okay, many people believe that. And I'm going to show you why that's not true. Okay, it's not true. It's only true half of the time. It's only true when x is positive. So if I tell you that x is negative 3, and I plug in negative 3 for x, plug in negative 3 for x, do I get an equivalent expression? No, those aren't equal. Okay, this is conditional. So this isn't true all the time. We have to have something that's true all the time. Really, it has to be the square root of x squared is the absolute value of x. That is a thing. That is a really important thing that many times is missed in earlier grades just because it's so abstract, right? Who would think about that? You know, people don't usually deal with stuff like that. But it's quite abstract. It's important to us, because it's going to make the difference in the answer to this problem right here. It's going to make the difference. And in knowing that these are equivalent, we also have to remember what the definition of absolute value of x is. We just covered it a few days ago, right? We know that the absolute value of x is a piecewise function. Remember? We know there's a definition. It's x when x is greater than or equal to 0, and it's negative x when x is less than 0. So when I have a radical that I am taking to infinity, positive or negative infinity, when I have a radical, I am going to have to use this concept, and I'm going to have to figure out which branch to use. Okay? So, let's begin. We know that this is true. Okay, this is true. Those are interchangeable. I can interchange them however I choose to help me. So when I come up with my form of 1 that I'm multiplying by, I'm going to multiply by the square root of 1 over x squared over 1 over absolute value x. Why did I do that? Well, because the numerator has the radical in it and the denominator doesn't. But that's still the number 1. They're still equivalent. Okay, are we comfortable with that? As comfortable as we're probably going to be right this minute. Okay, so now I'm going to distribute. So I have the limit as x goes to negative infinity. So in the numerator, I'm going to distribute that 1 over x squared underneath the radical. That's the only way I can multiply with the radical is with another radical. So that gives me x squared over x squared plus 3x over x squared minus 1 over x squared. That's what my numerator looks like. In the denominator, I'm going to multiply by 1 over absolute value x. That's an equivalent form. So I have 3x over absolute value x plus 1 over absolute value x. You kind of pause here for a second. Is everybody okay? Now we're going to clean it up. Let's simplify. So we have the limit as x goes to negative infinity. So we know x squared over x squared is 1. We know 3x over x squared is 3 over x, and this is minus 1 over x squared. Okay? Now, let's think about how to simplify. Now, this was confusing students earlier today. I hope you're with me. So I have got to determine which branch of the absolute value of x am I going to use. How do I do that? Well, what I have to do is I have to look to see what numbers are going to be put into this expression. What numbers, what kind of numbers are going to be put in here? Negative numbers are going to be put in here, right? We go back to our definition. Which of the branches belongs when the numbers are negative? The bottom one, right? Negative x. So when I simplify this, I am going, to take it out of absolute value, I'm going to use the bottom branch, the second one, because I have negative numbers. What would happen if we were going to a positive infinity? Well, I would use the top branch because we're only using, see, this tells me where to do, right? X is bigger than 0, x is less than 0. It tells me what to do. So I'm going to be using negative x. So this is going to be 3x over negative x plus 1 over negative x. All right, so now let's take the limit. So we know that this is going to go to 0. It's going to tend to 0. This is going to tend to 0, and that's going to tend to 0. We know that. What happens to that x over x? That just simplifies, right? Don't we cross that out? So my answer is going to be the square root of 1 over negative 3. Or if we know what the square root of 1 is, it's, 1. So my answer is really negative 1/3. What do you think my answer would have been had I gone to a positive infinity? Just 1/3, right? Just 1/3. So it really makes a big difference. Okay? Are we okay with that? All right. So now we move to the part of the lesson that we're just matching formulas. Okay, we're just matching formulas. So I'm going to write the formula. This is got the radical and it's got a number minus a variable. Okay, so that was that 1 over square root of a squared minus x squared dx. Okay, we're going to match it to that formula. Now the important thing is it has to have one thing squared minus one thing squared. I can't have, this 2 is going to be an issue. Alright, so what I would do is I'd pull the 10 outside the integral. Do you have to? No, you could leave it there, it's fine. But I'll pull it out there because I want it to look exactly like the formula. Got the radical there, everything. This quantity at the first part has to be squared. Well, 7 isn't squared, so I have to rewrite it to where it would be squared. So what could I square to get 7? Square root of 7, right? Square root of 7, square root of 7. So I have to write that as the square root of 7 squared. Okay, so that's I rewrote the first part. This second part has to be something squared. Certainly I think we can see that x works, right? But what about 2? Is 2 squared? No, it's not squared. How could I make 2 look like it's squared? Square root of 2, right? So this is going to be the square root of 2x. That quantity is going to be squared. Okay, so just for fun, you don't have to know this part, but this is just fun, right? Just for fun, I'll tell you what this integral equals, because I'm not talking about the other side. This would be 10, actually over root 2, arc sine of root 2x over root 7 plus c. Isn't that fantastic? That's what it would be. See that beautiful arc sine? Don't you miss it from last semester? I miss it. Okay, so that's just fun fact. Just a fun fact. Do you have to know that? No. I need you to be able to do this, because when you do this, you're going to be able to use the formula to do this. Okay, there's a formula involved. Calculus is all about formulas. So here, my formula is 1 over a squared. Oh, sorry. It says state what a equals. A is square root of 7. Okay. So my formula for this one is actually, this one's actually even easier, right? This is why am I using this formula for this one? Well, because it's got a plus and no radical, right? You don't have to memorize those formulas. I would give them to you. They're going to be on your daily work. They'll be on your homework. I'm just giving them to you. So don't need to memorize the formula. So I'm rewriting it as 5 times 1 over 2 squared plus x squared, and a would be 2. Okay? Are we okay with that? All right.